All right, for this video, I want us to focus on thinking about the amplitude and the period of our sine and cosine graphs. So I'm going to again use Desmos. So let's go ahead and share my desktop. So you should see Desmos there now. Okay, so we're going to start with the graph of the cosine function. So a couple of things to remember. Remember that to start with, the cosine function has a period of 2 pi. Because this pattern repeats every 2 pi units along the x-axis. Okay. Now, amplitude, remember, tells us kind of how tall this function is. So our amplitude, right, our function runs between -1 and 1. Our amplitude is half of that distance. So in other words, you can think of it as the height of a wave or the trough of a wave. So our amplitude in this case is 1 unit, okay? You can think of that as half of 2, from -1 to 1, half of 2. Or you can think of it, if 0 is our baseline, this goes up 1 unit to get to the height of our wave, or our periodic function. Okay, so our basic sine function has amplitude 1 and period 2 pi. Now what we want to do is we want to mess around with this function and see how we can change the period and change the amplitude. Okay, so now I want you to think back to when we had just non-trigonometric functions. And you may remember some stuff about graphing non-trigonometric functions. In particular, I know that those of you who have had me in class before, we did a lot with thinking about graphing functions. So I just want to do a little kind of review of that very, very briefly. So we're going to take a basic quadratic function. Okay, so the graph of f of x equals 2 times x minus 3 squared plus 4. Okay. And here's that graph right there. Now, you may or may not remember that this is a transformed graph of the basic x squared graph. This is our basic x squared graph. And if we're thinking about how we have transformed this graph, well, different parts of this function are going to tell us what we have done. In particular, this -3 that's inside with the x represents a horizontal shift. And it shows that we have shifted our function 3 units to the right. So this function has gone 3 units to the right. This +4 outside of our squaring piece tells me that I have done a vertical shift, or I've shifted this function up 4. So over 3, up 4, okay? And then this 2 outside is a vertical stretch. So it tells me that I've stretched up my function or made it kind of taller and skinnier than it was before. Now in particular, I want to focus in on this vertical stretch, okay, to start with. So when I multiply this function times 2, it gives me a vertical stretch. If I were to multiply times, say, 1/2, it gives me something that makes my function wider, okay? So it seems to be changing kind of the width of our function. And what I want to do is explore what happens when we do the same thing with our cosine function, okay? So here's our cosine function. I'm going to kind of zoom back in. All right, so there's our cosine function. Now, let's see what happens when we multiply this function by something like 2. So 2 cosine of x. Whoa, that looks a lot different. I'm going to make it a different color. So blue is the graph of 2 times the cosine of x. Let's go ahead for comparison, do the graph of 1/2 cosine of x. And again, I'm going to change the color so you can see it. Okay, so there's a lot going on there. We've got 3 different things happening. Our red graph is the graph of the cosine of x, just our plain old boring cosine of x function. Our blue graph is the graph of 2 cosine of x. We multiplied by 2 outside of the function, kind of in front of the function. And our green is 1/2, okay, 1/2 the cosine function. And notice what those have done. If we compare just our cosine function, so there's cosine, to our 2 times cosine function, it sure seems like we have stretched that function up. So that 2 represents a vertical stretching, but what that really is doing is, isn't that changing the amplitude of our function, right? Our amplitude went from 1, right? And it doubled and went to 2. So this function, 2 cosine of x, has amplitude of 2. Now let's look at the cosine of x function compared to the 1/2 cosine of x function. Well, again, this is a vertical shrinking or squishing down of our function. And what it really does is it changes the amplitude of our function, right? Our original cosine of x function, the red function, had amplitude 1. Our 1/2 cosine of x function has amplitude 1/2. All right, well, let's play around a little bit more. So there again is our graph of the cosine of x function, unchanged. What do you think is going to happen if we do 3 times the cosine of x? How is that going to change our graph? Well, if we think about this from a vertical stretching point, it's going to stretch our graph to 3 times its original height. If I think about this from an amplitude point of view, it's going to triple my amplitude, or I expect this function to go from -3 to 3. Let's see if it does that. I'm going to zoom out a little bit. Oops. Whoa, that did not do what I wanted to. Sorry, hold on. What is happening? I'm going to pause real quick and figure out what's happening. All right, sorry about that. Okay, so again, in red, we have our original cosine graph. Our blue graph is the graph of 3 times cosine of x. And it sure did change our amplitude, or make this function go from -3 to 3, which means our amplitude will be 3. All right, well, let's think about the cosine of 1/3. What do you think is going to happen? What will our function look like? And what will be the amplitude of our function? Well, hopefully you said that our function will be squished, or 1/3 of its original height. And that means that our amplitude is going to go from -1/3 to 1/3. So our amplitude is 1/3. All right, let's try just a couple more. So I'm going to put them up here. Let's do 2/5. And let's also do 9/4. Okay, so 2/5 cosine of x, that's where we're going to start. First of all, is this going to represent a vertical stretching, meaning our function is going to get taller? Or is this going to represent a vertical squishing, meaning our function is going to get kind of shorter than where it is before? Well, 2/5 is less than 1. So I use the analogy, if I squished you down to 2/5 your height, you would be shorter than you were before. And it sure is. Now, if I look, right, at my little period here, it goes from sorry, not my period, my amplitude, excuse me. My amplitude goes from -0.4 to 0.4. 0.4 is the same thing as 2/5. So this now has an amplitude of 2/5. How about 9/4? Well, if we multiply by 9/4, 9/4 is bigger than 1. So I'm expecting this to be taller than the original cosine of x function. And it sure is. Let's zoom out a little bit. So this goes from 2 2/5, which is 9/4, all the way down to -2 2/5. So our amplitude is going to be from 0 to 2 2/5, or 9/4. So it sure seems like to change our amplitude, we're going to use a multiplier outside of the cosine function. And we'll see that that's kind of going to be what we do. All right, let's talk next a little bit about the period and how we might change the period of the cosine function. Okay, so now I want to talk about changing the period. Well, one way we can think about changing a period is, right, we're trying to change sort of how our function looks horizontally. So we can almost think of this as horizontal stretches or horizontal shrinks. So let's take a look at what happens when instead of multiplying outside, we multiply inside. So before we were looking at cosine of x compared to 2 times cosine of x compared to 1/2 times cosine of x. Notice that now I've moved those multipliers inside of the argument of the cosine function. So what do we think is going to happen when we look at cosine of 2x? Right now on the graph is our original cosine of x function. It has a period from 0 to 2 pi. I'm going to go ahead and put that up. And I'm going to put those both in red just so we can see that that's the period of our original cosine function. And now let's graph cosine of 2 pi. Whoa! That's kind of hard to see with everything going on. I'm going to turn off our cosine function for a minute. And what has happened? Well, let's see if we can figure out what the period of this cosine of 2x function is. Now, a period, remember, is kind of one complete cycle through of this graph. So starting at 1, coming all the way down to -1, and going up to 1. So it looks like our period now goes between here and here. So there's one period of our function between x equals 0 and x equals pi. Again, I'm going to make those green. So there's one period of this function. So how does that compare to one period of our original function? Well, it's a lot smaller, right? So again, it's gonna get a little confusing on there, but I'm gonna look at, there's our original cosine function, period from 0 to 2 pi, and here's our cosine of 2x function. We've squished that function down, or kind of horizontally compressed it. So we've, excuse me, I'm sorry, horizontally compressed that function, or made the period smaller. All right. So now let's look at the opposite. What do we think is going to happen when we have 1/2 x inside the argument? The 2x squished our period down, made our period half again as much. What about this? Any guesses? Let's see. It looks like this function is now wider than it was before, or we've represented a horizontal stretch. I'm going to have to zoom out a little bit because I can't even see a full period of this guy. So now I just have the cosine of 1/2 x function graphed, and let's see if we can figure out what the period is. Well, starting at 1 and doing one full cycle all the way back over here to 1, it looks like the period of this guy goes from 0 to 4 pi. So our period doubled. Remember that our original period was 2 pi. This has period 4 pi. So our function cosine 2x had half as big a period. Our function cosine 1/2 x had twice as big a period. See if we can do this for something else. All right, let's consider, oops. All right, so before we looked at cosine of x, cosine of 2x, cosine of 1/2 x. Well, starting again with our original cosine function, let's look at cosine of 4x and cosine of 1/4 x. So before we start, let's make some predictions. Okay. Cosine of 4x, is that going to expand our period, representing a horizontal stretch? Or is it going to compress our period, representing a horizontal shrinking? Let's find out. Oh my goodness, that's almost painful to look at. So it's definitely squished down our period. Look, we have a lot more waves in between 0 and 2 pi than just 1. I'm going to go ahead and zoom in. Oh, I'm going to turn off our original cosine function. And let's see if we can figure out what the period of this guy is. Oop, I zoomed in too far. Okay. Well, a period goes from one wave top to another wave top. That's one way to think about it. So this period goes from 0, x equals 0, to pi over 2. Okay. So we went from a period of 2 pi to a period of pi over 2. Well, that's actually 1/4 as big. So let's again look at this. Another way to think of this is notice that our original period, 0 to 2 pi, now contains 1, 2, 3, 4 little waves. So we've actually compressed that, or made our period 4 times smaller. Okay, all right. So now let's look at cosine of 1/4 x. Cosine of 1/4 x. I'm expecting that to stretch out, horizontally stretch my function, or make my period wider, make my period longer. And since 1/2 made my period twice as long, I'm expecting 1/4 to make my period 4 times as long. So my original period is 2 pi. If I take 2 pi and multiply by 4, I'm expecting the period of this function to be 8 pi. Let's see if we're right. I'm gonna have to zoom out, way out. Okay, so here's one full cycle from 1 to 1 of this guy, starting at 0 and going to 8 pi. So the period of this would be 8 pi. All right. So let's do one more example set here and see if we can't figure out the period of things that maybe aren't so nice. So let's do 3/2. And how about 4/5? Oh, these are going to be kind of ugly, but let's see if we can't figure them out. Okay, so first of all, let's just think about, do we expect our period to be longer or shorter than our original period? Well, cosine of x we know has period 0 to 2 pi. cosine of 3/2 x, notice that that 3/2 is bigger than 1. Now what happened when we had cosine of 2x and cosine of 4x? For both of those, our periods got shorter, or our function was horizontally squished together. So I'm going to expect that this, we'll see my period get shorter or squish it together. Let's see. My period is definitely shorter. Okay. And let's see if we can figure out what that period would be. All right. Well, one thing that we could think about is we know that we can use our graph to come up with our period, right? So first, our period goes from 0 to 4 pi over 3. So our period is 4 pi over 3. In other words, we make one complete cycle every 4 pi over 3 units on our graph. Now that's handy, but we also want to come up with a way to just look at something and figure out what the period is without graphing it. So we're going to come back to that here in just a second. But let's look at our second example here, 4/5 x, so cosine of 4/5 x. Now remember, when we looked at 1/2, cosine of 1/2 x and cosine of 1/4 x, what did we see? We saw those periods get wider, our periods get longer. So I would expect this, 4/5 x, to get longer, for our period to get longer. Oh, and it did. Our period now goes from 0 to 5 pi over 2. Okay, so right now we've seen that our periods are going to decrease or squish down when we multiply inside by a number bigger than 1, and our periods are going to get wider when we multiply by a number less than 1. Now, the last thing that we want to do is we want to see if we can figure out how can we determine exactly what a period of a function is when we are looking just at kind of the function notation. I'm going to pause this for a minute and go to the board, and we're going to see if we can't work that out. All right, so here are the functions that we looked at and what we saw their periods to be, what we observed them to be on the graph. We want to come up with kind of an algebraic way to figure out what the period will be. Okay, well, one thing we saw is that when we had a number bigger than 1 as our multiplier, so in the case of cosine of 2x and the cosine of 4x, right, our period decreased or got smaller. These represent a horizontal shrinking. Okay. Well, the original period of cosine of the original period of cosine of x was 2 pi. When we shrink that period, we're going to divide by kind of this factor here. 2 pi divided by 2 gives us our new period of pi. That will also work over here. Our original period of cosine was 2 pi. We are horizontally shrinking this by a factor of 4. So we're shrinking our period by a factor of 4. So dividing 2 pi by 4, 2 over 4 is 1/2, where this reduces to pi over 2, which was exactly the period that we saw. Okay, here, right, our periods increased, or this represents a horizontal stretching. So what we can do here is we can think about our original period, 2 pi, and we're really multiplying kind of by this factor of 2. This represents a horizontal stretch of 2. So we can think of this as 2 pi times 2, which gives us that period of 4 pi. Now this is going to work really well for unit fractions, 1 over 2, but it's going to cause some problems over here. So one way to kind of simplify this, and also to make it so we're doing the exact same thing anytime we find the period, is notice that if I take my original period, 2 pi, and divide by 1/2, that is dividing by this multiplication factor, the nice thing about that is it's the same thing I do here, 2 pi divided by 2. 2 pi divided by 4. It means that I am dividing fractions, but remember that dividing by a fraction is the same thing as multiplying by the reciprocal. So 2 pi divided by 1/2 is the same thing as 2 pi times 2, which again gives us that 4 pi. Applying that same idea over here, we can do 2 pi divided by our horizontal stretching factor, so 2 pi divided by 1/4, which is the same thing as 2 pi times 4 over 1. 2 pi times 4 gives us 8 pi, which is exactly what we saw the period to be on our graph. Now, let's apply that to those last two. Okay. So let's consider the period of cosine of 3/2 x. Okay. Well, our original period, the period of cosine is 2 pi. Okay. We're going to divide that by this factor here, 3/2. Okay. 2 pi divided by 3/2 is the same thing as 2 pi times 2/3. Dividing by a fraction is the same thing as multiplying by the reciprocal. I can think of 2 pi as 2 pi over 1. So I have 2 pi over 1 times 2/3. 2 pi times 2 is 4 pi. 1 times 3 is 3, so our period is 4 pi over 3. And remember, that's exactly what we saw when we looked at the peak of one wave to the peak of the other wave. Okay. Let's do that for our last example there. So we want to find the period of the cosine of 4/5 x. So we're going to take our original period. The period of cosine is 2 pi, and we're going to divide by this horizontal stretching factor, 4/5. So that's 2 pi divided by 4/5, which is 2 pi, you can think of that as 2 pi over 1, times 5/4, which is 10, 2 times 5, pi over 4, 1 times 4. A little bit of simplification gives me 5 pi over 2. So our period is 5 pi over 2, which again is exactly what we saw on the graph there. All right, so that's kind of our introduction to amplitude and also period and how we can change the amplitude and period. As we move on, we're going to add in horizontal shifts. So right now we can change these guys by changing their amplitude, stretching and shrinking their amplitude, by changing their period, stretching and shrinking them this way. We're also going to see how we can move them horizontally and vertically, and then we can also reflect these.